So before we start looking at the simpler projectile worksheet, I just want to go over where our formulas come from for this worksheet. So with a simple projectile, we're taking a projectile like this, right? Like the marble in the lab. That's directed off the table with an initial velocity in the x direction only. And the marble is going to take this path off of the table, which is sort of like a parabola, and it's going to travel some range delta x and start some delta y above the ground. Now, the reason it's a projectile is because the only acceleration it experiences is the acceleration due to gravity, which we can call g, but it's going to be downward. And that's it, right? And so the formulas we're gonna use for this are gonna be our K formulas, but they're gonna both look slightly different. And so what we're gonna do is we're gonna split this motion of this projectile as this marble travels through the air, just like this, until right before it hits the ground, right? Because we always stop the motion right before contact. And let's look at both directions. Let's start with the x direction. So in the x direction, we'll go ahead and write K2. Now, what we know about a projectile in the x direction, and first of all, you might have noticed I did something slightly different this time, is that I labeled the VI and I labeled the A as being in the x direction. So one of the themes, or a couple of the themes of this chapter, one being that you can talk about the x direction set independently of the y direction. So for a projectile, you can separate the two directions. You can analyze the x direction independent of the y direction. And furthermore, you can write your K formulas for one direction only. And time is the bridge between the two directions. All right, hopefully that's easy for you to see. I know I'm not too zoomed in there. But all right, so those are some of the themes of this chapter that we're dealing with here. So we're writing the K formula for just the x direction here, and I notice I added subscripts. So first of all, another important idea of this chapter is that projectiles don't accelerate in the x direction, right? So because of that, this term over here from the expression is 0 times 1/2 times t squared, right? So this is just going to be 0. And our K formula shortens to just this. So this is K2 in the x direction because the rest of our equation is 0. Okay, so I'm going to go ahead and add that below. Projectiles don't accelerate in the x direction. All right. All right, so far so good. There's the x direction right there. What about the y direction? Let's go ahead and write K2 in the y direction. Let me get a little more room here. So just like before, I'm going to go ahead and write K2. But this time I'm going to say delta y is equal to VIY times t plus 1/2 AY times t squared. All right. Now, if we go back up and look at this motion, and the reason I call it simple projectile motion is because we don't have any initial velocity in the y direction. Notice that it's all about the marble when it leaves the table, right? We're interested in when the marble's in the air and has a constant acceleration of g downwards. So so the VIY is 0 here. And so we can update this K formula right here with VIY is 0. So let's go ahead and do that. So if that's 0, then this whole term here is 0, and we can rewrite our formula. And this is exactly what you've done in the last 2 labs. We also know that since down is negative, delta y and AY are going to be negative. But furthermore, we know that, let me go ahead and write this. I'm going to go ahead and write these negative signs. We know that AY is G. But if down is negative and G points downward, then we have to make G negative. If you just said down is positive, then obviously delta y and G would both be positive, and we'd be at the same point, because what we're going to see here is that the 2 negative signs are going to cancel, right? So we're not worried about this negative sign or this negative sign because they're going to cancel away. Why is delta y negative? That's the one that I always thought was a little trickier to talk about. The reason delta y is negative is because if you think about what delta y means, right, and the final position in the y direction of this marble is going to be 0 meters, and maybe the initial position is, I don't know, 0.93 meters. I'm just making something up. It's roughly the height of a lab table. Then you can see that delta y, because down is negative, or down is less than the 0.93, right? You can see that we plug 0 in here and plug 0.93 meters in here, you can see where that negative sign comes from. And that explanation always worked a little bit better for me, because I didn't like just saying, oh, down is negative and therefore delta y is negative. So I liked seeing the numbers and prove to me that delta y is negative, because the numbers themselves are not inherently negative, right? Yeah, okay. All right, so let's come back to this. Let's go ahead and solve for t. We're going to write an expression for time. This is a really important formula in AP Physics. This K2 in the y direction solved for time with no initial velocity. It just shows up a lot on problems. So anyways, let's multiply here both sides by 2. Do that. Cancel off Keep using blue for canceling. 1/2 times 2 is just 1. So we'll go ahead and rewrite here. So we have 2 delta y is equal to gt squared. Divide both sides by g. T squared is equal to 2 delta y over g. Square root both sides. Gets rid of the t squared. Square root the whole thing. So we end up getting our answer here, which we had in previous labs, as t is equal to the square root of 2 delta y over g. So what we have are two formulas, both based on K2, that don't look like K2. Whoops. That I want to mention because I think students sometimes think these are new formulas, right? Because they show up so much. This is not a new formula. This is not a new formula right here. All right. They are both just K2, and one is solved for t, one is still solved for delta x, but you can see where they come from, right? And so we have this formula right here for the delta x direction, or the x direction, which is going to give us the range, or how far something goes. So sometimes we like to call delta x here, this variable right here, we like to call this the range. And then we can also calculate how long a marble is in the air here with this formula right here for time. And notice that time is based on the y direction. That's another theme in this class, that the time a projectile is in the air is determined by the y direction. So I'm going to write that down. Hopefully you can see that. It's getting a little tough to read that. Time a projectile is in the air is determined by the y direction. All right, so hopefully you can read all those statements. I know I wrote them and they're kind of small, but yeah, I'll try and bring them up throughout the videos as we work on things. Okay, so two formulas to work on these simple projectiles, and that's really what you're going to do down here. So I'll go ahead and do a couple for you, and then I'll leave you the rest to do. All right, so here we have a lab. You can think of these all as being like lab tables, or marbles rolling off of a lab table or a building. I guess a lab table probably wouldn't cut it with some of these heights. But I think the first one we can consider maybe a tall lab table. So in this first one, you have a height here, a delta y value of 2 meters. You then have a marble up here that's about to roll off, and it's got a V. Sometimes instead of using VI, you can use V naught, which is I like using sometimes. It's a little fancier than just using VI. So we can say V naught X. You can put a comma in there too if you want, in between the naught and the X. Sometimes I do, sometimes I don't. So if you don't want to throw that comma in there, you don't have to. So V naught X is going to equal, I think they tell us 20 meters per second, which is pretty fast, like 50 miles an hour or so. All right, so we want to know how long is the marble in the air, right? And once again, for time in the air, we said we look at the y direction. So we're going to end up using our formula from above, which was, I would write this out every time just because it does help you remember. and then we'll plug in what we know. I think we said delta y was 2 meters. Divide by 9.81. All right, notice the units, right? You can see from here that meters are going to cancel. And then we have a fraction in the bottom of our fraction. So the second squared actually is going to float up to the top. And that should make sense, right? Because you have something like this, right? You have meters on top, then you have meters per second squared on bottom. You're going to flip and multiply by this fraction that's on the bottom. You're going to multiply by its reciprocal. So the reciprocal of that would be second squared over meters. And you can erase this down here. So we're left with this. Meters cancel, and you have the second squared on top, which makes sense because you're going to square root and get seconds. All right, so when you have this, I do like to be clear here that we want to get one number underneath before we square root. So let's go ahead and keep simplifying here. So we have 4 seconds squared over 9.81. Now, whoops, we got rid of those meters. Do you have to show all these steps? I would at least show the first setup step. But I always tend to show a little more than I need to. I don't know what happened to my calculator. I'm going to go snag it. Hold on one second. All right, so 4 divided by 9.81 is equal to 0.4077. And that's going to be seconds squared. And then we'll square root that answer. Now, even though I rounded it right there, I'm gonna square root the entire thing in my calculator. It's usually a bad idea to round early. So I'll say second square root answer. Now I'm getting 0.638. So I'm gonna go ahead and round that to 0.64 seconds. Okay, so there we have it for the first problem. Range here. Once again, we're looking at the x direction. We want to know what delta x is. So we're going to use K2 in the x direction, which is this. Delta x equals VIX times t, right? The rest of K2 is gone because AX is 0. So we're left with just this shortened equation. We'll go ahead and plug in what we know. And notice we can use this equation. We went from the y direction right here, right? We started in the y direction. We are now in the x direction. And what we're doing here is we have a bridge, right? What's that bridge between these two formulas? You can see that the bridge here is time, right? That we're going to take that time value and plug it in right there. And that's going to connect our two directions. So I think they told us the VIX is 20. So we'll go ahead and plug in 0.64 seconds. You can also see, if you're paying attention to the units, seconds are going to cancel. And we'll just multiply that by 20. I'm getting about 12.8. Just going to check it one time. I think a better answer might be 12.771, but I'm going to go ahead and round just to 12.8 and call it good. All right, so there you have it right there. Let's go ahead and do one more. And you can see where you might want a separate sheet of paper for this. This is kind of I don't know. I'm already running out a little bit of room, but I know some of you guys don't really care and like to write small. All right, 5 meters is about 15 feet. So maybe this is like a small building or something. And this time, I don't think I can draw a building very well. You have a marble or something up here. I don't know, maybe it's a soccer ball, who knows. All right, and it's gonna roll off of this shed or something with a VOX of 8 meters per second. And the height here, the delta Y, is equal to 5 meters. Now, drawing is a super important first step in a lot of physics problems. So I always recommend it. I think it's just a good habit to get into. I know it takes more time, but yeah, I don't know. It's a smart thing to do. Okay, so want to know the same thing, time in the air, right? So even if you don't want to say write out this formula every time, right here, I'm going to highlight it. If you don't say want to write that out, always write out the setup step, which is this, right? It's the formula with those numbers applied to it. I recommend writing both out right now just because you're learning the formula and help you start to memorize it. But you know, if I was doing this for myself, maybe I'd skip that step and go right to the setup step, but that's because I know the formula, right? It doesn't hurt to write it out. All right, so go ahead and write that out. Square root of 2 times delta Y, which I think we said was 5 meters, divided by 9.81. All right, so now it makes sense why we're going to get seconds here as a unit. 2 times 5 is 10. 10 divided by 9.81 is 1.019. We'll square root that. Second square root, second answer. I'm getting about 1.01 seconds. Whoops, where's my... This pencil doesn't want to write. 1.01. All right, good. Now we go to the x direction, right? This was just the y direction we just worked off. So now we'll look at the x direction, and we got our k2 in the x direction. Delta x equals VIX times t. Notice I wrote it the fancier way, and that's okay too. Want to know what delta x is? We know that V naught x, what was it, 8? Yeah, it was 8 meters per second. And now we're going to plug in the time from the y direction. Remember I said time is the bridge, right? That's going to go right there. Okay. So we'll go ahead and put in 1.01 seconds. Is that just going to be 8.08 if I multiply that? I think it is. I better check, though. Yeah. I don't know why I don't trust myself. Just traumatized by too many math tests where things didn't work out the way I wanted, I guess. All right, 8.08. Notice the units, right? Seconds are going to cancel away. Second on top and on bottom. And I hate writing it like I did right there with the meters per second, but that is meters over seconds. So yeah, that's why I don't like writing it that way. All right, because sometimes students don't see that. So 8.08 meters. Okay. So that's it. I worked out 2 of them for you. You got the other ones you can complete on your own. And I think there's 10 or 11 here. Yeah, so I'd say, let's see here. Yeah, I'll probably shorten it a little bit for the assignment, but at least you know what you're doing now, and you can work on the rest. All right, have a good day.